Hello everyone, welcome to 16C. My name is Alan and I'm the instructor of the course. We have 3 lectures a week, Mondays, Wednesdays, and Fridays, and 1 web work assignment after each lecture. We also have 1 quiz per week. I'll send more information about the homeworks and the quizzes later today. We still don't have Canvas. The Canvas page still hasn't been set up. I've already emailed the department. Hopefully it'll be fixed in the next day or so. But for the time being, I'll just have to send everything through email. For the webworks, I think you need Canvas to access them, so uh, you probably can't see the homeworks for now. What I'll do is just I'll extend the deadlines of the first few webwork assignments. That way, you guys will have enough time to finish them. Okay. Now the textbook that we're using is this Calculus and Applied Approach by Larson. I believe the latest edition is the 9th edition, but I have the 8th. So if you have an older version, it shouldn't be too big a problem because I mean all the homeworks are on WebWork, and we're not doing specific problems in the book as homeworks. Okay. All right, so we'll start with differential equations. I think this will be probably 2 to 3 lectures, and then after that we'll move on to chapter 7 of the book, which is, I believe, three-dimensional coordinates and stuff. Okay, all right, let's start the lecture today. Differential equation. I'm sure you've all seen differential equation before, so this is probably just a quick recap for a lot of you. Now, what is a differential equation? A differential equation is, by definition, is just any. Okay. By definition, it's just an equation that involves differentiable functions and its derivatives. Sorry, like I said in the previous email, I'm still in the hotel, so I don't have my iPad with me. I just have a writing pad, so sorry, please excuse my writing. So this is a differential equation. It's just an equation that involves differentiable functions and its derivatives. Let's see an example. A simple example would be something like this. Y prime plus 2y equals 0. Okay, so y, say, is a function of x, then y is a differentiable equation, and y prime is the derivative. Let's see if we can make this a little thicker. Anyways, all right, now look at this example we have. This is y prime plus 2y equals 0. If you want to solve it, what you will end up with is what we call a general solution. Now, what is a general solution? Typically, I'm sure you've seen it before. Typically, a general solution involves one or more arbitrary constants, like c. Usually, we use c to denote an arbitrary constant. If you end up with more, we sometimes use d and e and stuff. Okay, so general solution is just a family of solutions. For example, if you solve this equation right here, you won't end up with just one solution. You will end up with a family of solutions. So that's what general solutions is. A family of solutions. For example, y equals c times x squared is the general solution of xy prime minus 2y equals 0. Right, so this is the general solution, and like I said, there's an arbitrary constant c involved, and that's why it's a family of solutions, because c is an arbitrary constant. You can take it 1, 2, 3, so it gives you infinitely many solutions. Okay, and particular solutions they are solutions obtained from the equation, the differential equation, and initial conditions, okay, which I'll abbreviate IC, initial conditions. For example, y equals 2x squared, we're going to use the same differential equation, but with an extra condition. The initial condition, we now have a specific choice of c, as you'll see. Y equals 2x squared is the particular solution of xy prime minus 2y equals 0, and y of 1 equals 2. Note that the equation itself will only give you a general solution. You will end up with the arbitrary constant, but with the help of an initial condition here, we can plug the initial condition into the equation and solve for c. So we have a particular solution, y equals 2x squared. Okay. Note here, I simply told you y equals cx squared is the general solution of the equation xy prime minus 2y equals 0. But why, right? It's actually very simple. So all you do is you plug the equation into, you plug the solution that you want to check into the equation, and you confirm that the equation holds. So let's see an example here. Check solutions. Example 1. Confirm that, check that y equals c times x cubed is the general solution of the equation xy prime minus 3y equals 0. Now all you do is you plug this equation, you plug the solution into the equation. So if y is c times x cubed, then what is y prime? We have y equals c times x cubed, and if you differentiate it, you get y prime equals 3 times x, 3 times c times then x squared. Right, now we plug it in, we get xy prime minus 3y is x times 3c x squared then minus 3c x cubed. Now x times x squared becomes x cubed, so they cancel out, and we get 0. So we just confirm that xy prime minus 3y is indeed 0, and we're done. That means this is indeed the solution of this equation. Okay, let's try another example here. Check y equals e to the x squared is a particular solution to the initial value problem. So an equation with initial condition is what we call an initial value problem. Okay, y prime minus 2xy equals 0, and y of 0 equals 1. Okay, again, we first calculate y prime. If y is e to the x squared, then by chain rule, y prime is e to the x squared times the derivative of the exponent, which is times 2x. Okay, now plug it in, we get y prime minus 2xy equals 2x times, I just exchanged these, so it's 2x times e to the x squared, then minus 2x times e to the x squared, which is 0. So we've checked that the equation indeed holds. Now, since this is an initial value problem, we need to also check that the initial condition holds. To do that, we simply plug 0 into our solution. We get y of 0 equals e to the 0 squared. Now 0 squared is 0, and e to the 0 is 1. So we have y of 0 equals 1. And that implies this is indeed the particular solution to this initial value problem. Next, let's look at another problem, and this time we'll sketch the solutions. The problem is this. First, confirm that two y squared minus x squared equals c is the general solution. I'm just going to write gen solutions of 2 y prime minus x equals 0. Sorry. Then sketch solutions for c equals 0, and then plus minus 1. Okay, note that, so first, since an arbitrary constant is involved, obviously this is the general solution. Note that this is not, this is what you can call an implicit solution, so it's not written out as, say, y equals something about x. You can certainly change this to that format. You will get y equals plus minus square root of 1/2 c plus x squared, but you can also just leave it like this. Okay, just because this format looks a bit simpler without the plus minus symbol. Alright, to check that, since we have the implicit solution instead of the explicit formulation, y equals something, instead of calculating y prime, we can just differentiate the entire equation by x. I mean, you can, the other way to do it would be just to, for example, so that's say method 1 is just to change this into an explicit formulation that depends on x only. You get y equals plus minus square root of c plus x squared over 2. And then you calculate y prime and plug it in and just go through the same process we went through before. Or an easier way to do this problem would be this. Just differentiate this implicit solution with respect to x. So we get d dx. Essentially, I'm saying this. Differentiate this entire equation not c, I mean. Okay, now what's on the left? If we differentiate 2y squared, what do we get? We get 4y times dy dx, right? And if we differentiate x squared, we get 2x. Here we have dy dx because y is a function of x. This is the chain rule. Okay. Now since c is a constant, what becomes the derivative of a constant? It's 0, right? So we have this, and divide both sides by 2, we get 2y times dy dx is just y prime, right? So it's 2y y prime minus x equals 0. And we've confirmed that this is indeed the solution of this equation. Now let's sketch the solutions for c equals 0. Now if c is 0, then what do we have? We have y equals, you can plug it into this one or this one, either way is fine. If you plug it into our original formulation, we get 2y squared equals c, or equivalently, y equals plus minus square root of c over 2, right? So it's just two straight lines. Oh, c is 0. What am I doing? I meant, sorry. If we plug in c equals 0, we get 2y squared minus x squared equals 0. And that is equivalent to y equals plus minus square root of x squared over 2. Or this is the same as plus minus 1 over square root 2 times x, right? So you just get two straight lines here, like this. Okay, so this is the case for c equals 0. And let's look at c equals 1. If c equals 1, then you get 2y squared minus x squared equals 1. Or if we move the minus squared to the right, so add x squared to on both sides, we'll get 2y squared equals x squared plus 1. And let's just leave it as it is. So it's just 2y squared minus x squared, because I think that's the general formula for hyperbolas, equals 1. This is the formula of a hyperbola, and it looks like this. This is just a rough sketch. Now, if you want to be specific about it, to characterize a hyperbola, you need a couple of things. So the top and bottom of the two curves, and then the asymptotic behavior. How you can do it is look at this curve. This is characterized by y being positive, right? When x, the lowest point obviously happens when x equals 0, and then this point would be just square root of 1 over 2. And similarly, this would be minus square root of 1 over 2. And to figure out the asymptotic axis, all you have to do is let x go to infinity. Well, if x goes to infinity, then 1 is relatively small. Then you have 2y squared approximately equals x squared, right? So you get y equals square root of x squared over 2. So this is this one, and this one would be y equals minus square root of x squared over 2. Okay, and at last, let me add a page here. Let's look at c equals minus 1. Then what do we have? We have 2y squared minus x squared equals minus 1. If you multiply minus 1 to both sides, you get x squared minus 2y squared. This is 2y squared equals 1. This is again a hyperbola just pointing sideways, so it's two curves pointing towards the positive and negative sides of the x-axis. Okay? And same story to figure out the coordinate of these 2 points, the leftmost point and the rightmost point of the 2 curves. You just plug in y equals 0, you get x equals plus minus 1, so this is minus 1, 0, and that's plus 1, 0. And the asymptotic behavior, again, you look at when y goes to infinity, then x squared is again approximately 2y squared. So the asymptotic axes are the same as the ones before. Okay? All right. Now, so far, we've only talked about confirming solutions. We never really solved any equation, right? So all the examples I've given so far are about are confirming solutions of a given equation. So I'm giving you the solution. I just ask you to check it. Now, of course, for most part of differential equations is actually solving the equation, finding a solution on your own. How do we do that? That's a lot more complicated than checking a solution. So here we first talk about a special type of equations, which is called the separable equation. Now, the separable equation is a differential equation that looks like this: dy dx equals f of x times g of y. Now, the reason we call this separable equations is because we can separate the part about x and the part about y. Now, I know that dy dx is a thing on its own. It stands for the derivative of y with respect to x. But for a moment, let's consider this as a fraction, dy divided by dx. Okay? Then you can turn this into dy over g of y equals f of x dx. Now we've successfully separated the part that depends on y only with the part that depends on x only. That's why we call this separable equations. Okay. Now, of course, this is not an entirely rigorous formulation. Just because dy dx is derivative of y with respect to x, it's not dy divided by dx. But you get the idea. This is why we call it separable equations. Okay, to solve the separable equations, we use a method called the separation of variables. It's exactly what I have outlined here, but we need to make it a little bit more rigorous, just because dy dx is not dy divided by dx. This is done by fundamental theorem of calculus, or this is done by the rule of change of variables. Okay, so suppose we have the equation dy dx equals f of x times g of y. Then we have 1 over g of y times dy dx equals f of x. Right, I just divided both sides by g of y. We have this. Now integrate both sides with respect to x. So we have 1 over g of y dy dx. Integrate this with respect to x equals the integral of f of x with respect to x. Okay? Now, by change of variables, we know that, or by chain rule, we know that when you integrate dy dx with respect to x, you get y. Okay, so this is 1 over g of y dy f of x. If you're not sure why this is true, just this is simple application of chain rule. Remember U substitution? This is exactly how U substitution is done. Except U substitution is going the other direction. You have something like this, and then you find an x such that you can add a dy dx in there. So this direction would be U substitution, but now we're going in this direction. This is just a simple application of chain rule. Okay? All right. Now, since we know what g is and we know what f is, we can just integrate both sides, and we get an equation about y equals an equation about x. Again, this may not be an explicit solution. You may get something like e to the y plus y squared plus y cubed equals something about x. So you may not be write it out in a very neat way, y equals 2x plus something. But it's a solution nonetheless. It gives the relation between y and x. It's an implicit solution, and if it is succinct enough, you may be able to get an explicit solution out of it. Okay, let's see a couple examples. First, let's solve dy dx equals x over y squared plus 1. Okay, so in this case, our if you want to apply this formula right here, if you want to apply that formula right here, then what you can write is f of x equals x, and our g of y. Remember that g of y is not y squared plus 1, because the right hand side is supposed to be f of x times g of y, so g of y is 1 over y squared plus 1, and then you just apply the formula. The formula was g of y dy, 1 over g of y dy equals the integral of f of x dx. In the next example, I'll skip the construction of f and g and just group the terms that depends on x and the terms that depend on y directly. Okay. But in this problem, I'm using the same formulation, f and g, and write it out that way. Okay. Now, if g is 1 over y squared plus y, what is 1 over g of y? That's just y squared plus 1, right? So we have the integral of y squared plus 1 dy equals the integral of x dx. Now, remember that both of them are indefinite integrals, so you'll get a plus c at the end. The left hand side is y cubed over 3 plus y, and the right hand side is x squared over 2 plus c. We only need one arbitrary constant c, because if you add another arbitrary constant d right here, all you have to do is just subtract d on both sides. Since c and d are both arbitrary, then c minus d is again arbitrary. So we're okay with just having 1 here. Okay, so when you have two indefinite integrals in the equation, you only need one arbitrary constant. This is what I meant when I say you may not get an explicit solution out of it, because it's hard to derive the equation y equals something out of it. So when that's the case, you can just leave it like this. Okay. Let's look at another problem. Number 2, solve e to the y times dy dx equals 2x. Same story. Let's group all the terms that depends on y and all the terms that depends on x. So we have e to the y times, it's actually grouped already, so e to the y times dy dx. Let's integrate both sides with respect to x. So we get this, and equals the integral of 2x dx. Remember that by chain rule, this reduces to dy. So we have e to the y dy equals 2x dx. Now the integral of e to the y is just e to the y. The integral of 2x is x squared, so you have x squared. Now since this is indefinite integral, you have a plus c at the end. Notice that in this case, it is easy to get an explicit solution, right? You just take the logarithm of both sides. So we have y equals ln of x squared plus c. Okay. So basically, I just want to say this. Basically, the rule is, if you think an explicit solution is very hard to obtain, then you just leave it in this form. If, for example, you have an equation, if you get to an implicit solution like this, and you realize it is very easy to get an explicit solution out of it, then you should do it and write out y explicitly in terms of x. Okay, last, let's look at an application of the separable equations. That is the modeling of national income. Let's define a few variables. First, y is national income. And a is income spent on necessities. And b is percent of remaining income spent on luxuries. Okay, then one common model used in economics is this: dy dt equals k times 1 minus b. Remember that b is percent of remaining income, so b is a number between 0 and 1. 1 minus b is always non-negative here. And then y minus a. Okay, so let's add the restraint here. So that means b is larger than or equal to 0 and smaller than or equal to 1. And again, A is income spent on necessities, so we're assuming that people don't raise debt here. That means A is smaller than or equal to Y. Okay, so both of these terms are non-negative. In this model, T is measured in years. T is in years. So dy dt is the rate of change of national income. And we assume A and B does not change as time goes on. So the income spent on necessities and the percent of income spent on luxuries remains the same every single year. And then this will be the model: dy dt equals k times 1 minus b times y minus a. Okay, let's solve this and see what happens to y. Well, y minus a is the only part that depends on y, so we have so let's divide both sides by y minus a. We get 1 over y minus a times dy dt equals k times 1 minus b. Notice that k times 1 minus b is just a constant. All right, let's integrate both sides with respect to t. Again, dy dt times dt becomes dy, right? So we get the integral of 1 over y minus a dy equals the integral of k times 1 minus b dt. Now, since we know that a is smaller than or equal to 0, then y minus a is positive. Then we have this the integral of the left hand side is ln of y minus a. And the right hand side, since k times 1 minus b is just a constant, we get k times 1 minus b. And of course, an arbitrary constant at the end. Okay, and let's call that constant C1. You'll see why I call it C1 in a minute. To get the explicit solution, we exponentiate both sides. So e to the this equals e to the this whole thing. Now e and ln cancel out, right? So the left-hand side, we're just left with y minus a. And the left-hand side, remember that, here's the, let me write a simple rule here. Remember that we have the exponential rule e to the, say, a plus b equals e to the a times e to the b, right? This is the product of exponentials. So similarly here we have this is e to the c1 times e to the I forgot a t here. Sorry. Let me rewrite this. T and then plus c1. Then e to the k times 1 minus b times t. Okay, now since c1 is an arbitrary constant, then e to the c1 is again an arbitrary constant. Let's just call that c. Okay, so this is why I call this c1, just to differentiate, distinguish this from the this arbitrary constant c, times e to the k times 1 minus b t. Okay, and finally plus a on both sides, we get y equals a plus c times e to the k 1 minus b t. Okay, so we see that as time goes on, y is actually a function that increases, well, it depends on whether you pick a positive or minus positive or negative k. If k is positive, then y increases exponentially, and if k is negative, then y decreases or you can say y decays exponentially, because 1 minus b is always positive, and since this is a actual real world example, t is not negative, right? It's the number of years. So as time goes on, t becomes large. 1 minus b is not negative. So y either increases or decays exponentially, depending on the sign of k. Okay? All right, so that's all we have to talk about today. I'll send announcements soon via email, and I'll see you on Wednesday.